In this question, we are going to show that two finite dimensional vector space U and V over the field are isomorphic. So we have to show that these are isomorphic if and only if the dimension of U equal to dimension of V. Okay. So suppose I take this dimension of U equal to dimension of V, I will try to show that they are isomorphic. So I take this as the basis of U, which are linearly independent, and this is the basis of V. So we try to define a mapping from U to V, defined as this. So we have this T equal to summation I equal to 1 to N alpha I EI equal to summation I equal to 1 to N alpha I EI thus. So we have here this, we take let U1, U2 belongs to U. So I take two elements from U, then these elements can be written as this. So we have T U1 plus U2. So we take T U1 plus U2, this can be written as T of summation I equal to 1 to N alpha I EI plus summation I equal to 1 to N beta I EI. So summation I can take common, I can add the coefficients. So we have here like this. So according to the definition of T, so this is sent to summation I equal to 1 to N alpha I EI dash. So this will be sent to summation I equal to 1 to N alpha I plus beta I EI dash. Okay. So we have this. So you multiply this one in this way. So if I reverse back the definition of T, I'll get this. Okay. This also in the same way. So we have here TU1 plus TU2. I take one element in U, so this is an, and I take one scalar in the field. Then we have here T alpha U equal to T alpha summation of this alpha you multiply here, so we get alpha lambda I. Then I'll apply the definition of T. So this is sent to summation I equal 1 to N alpha lambda I EI does. So we'll send to this EI does. Okay. So we have here alpha is a scalar, it will come out. So we have summation I equal 1 to N lambda I EI. So this is, if I reverse back the definition of T, so this will get T summation I equal to 1 to N lambda I EI, which is equal to, this is nothing but U. So we get equal to alpha TU. So this shows, this two property shows that T is a linear transformation. So we have shown the linear transformation. Now we try to show the kernel consists of only 0 element. So we took the kernel. I think that this is the definition of kernel. So I take U belongs to U such that TU is equal to 0. So we have T summation of I equal to 1 to N lambda I EI is equal to 0. So by the definition of T, we can write this as summation I equal to 1 to N alpha I EI dash is equal to 0. Okay. So here's, if you check here, these EI dots are the basis of V. So these are linearly independent. Since this set is linearly independent, the scalar should be 0. So we have here alpha I equal to 0. So we'll get here alpha I equal to 0 for all I equal to 1 to N. So we have U belongs to U. And this consists of only 0 element. Okay. So therefore T is 1, 1. So we have proof since it consists of only 0 element, this T is 1, 1. Okay. Now I'll take one element in V, then this element can be written as a linear combination of the basis element. So by the definition, if I reverse back the definition of T, so this can be written as T summation I equal to 1 to N lambda I EI. And this is an element in U, so we get TU. So where U this is this, and which belongs to U. So we have shown that T is onto. Okay. So we have shown T is 1, 1, T is onto, and T is a linear transformation. Hence, these two vector space should be isomorphic. So we have shown here, these are isomorphic to each other. Now we'll try to prove, using this condition, if they are isomorphic, we'll try to prove that they have the same dimension. So I take the basis of U to be this, and I take one element in V. Now since T is onto, it is isomorphic, means it is 1, 1 and onto. So since T is onto, that I took an element here, so there should be an element here also. Okay. So there exists an element U belongs to U such that T of this element should be this V. So we have here T of U equal to V. And U can be written as a linear combination of the basis element here. So we have here summation I equal 1 to N alpha I EI, which is equal to V. So this summation you can take out. So we have alpha I T of EI, which is equal to V. Okay. Now we can see here from this line we can say that any element of the vector space V can be written as a linear combination of this DEI. Okay, they can be written as this, means this set is spans this vector space. This set is spanning the vector space V. Okay, now our aim is only to show that this is linearly independent or not to become the basis. So we'll try to show this is linearly independent or not. So we take the linear combination of this, and this I take equal to 0. So where alpha I belongs to the field. Okay, now this I'm writing in summation, so we have this. Since T is a linear transformation, it can come outside, so we'll have T summation I equal to 1 to n alpha I ei equal to 0. Okay, now this is equal to 0 means this will belongs to kernel of T. Okay, now since T is 1 1, kernel of T consists of only 0 element, so this element should be 0. Okay, this of this is equal to 0 means this element should belongs to kernel. So kernel, this belongs to kernel, and since T is 1 1, kernel is consisting of only 0 elements. So we have here 0. So this element should be 0. Now we got this is 0, and this is nothing but the basis of U. E1, E2 till En are the basis of U. So these are linearly independent set. So this is a linearly independent set, so the scalar should be 0. So we got here alpha I is equal to 0 for all I equal to 1 to n. So we have shown that all the scalars are 0. So this set, okay, this set is linearly independent. So since this spans V as well as it is linearly independent, this becomes the basis of V. And if we count the number of elements here, okay, if we say here, the number of element here, it is n. So the dimension of V is n as well as dimension of U is n. So they have the same dimension. So we have proved the required question. Now here, in the next question, we have this. See here. Let V be a finite dimension vector space and F is a mapping from V to B be a homomorphism. Show that F is 1 1 if and only if F is on 2. Now we take a vector space from V to V, which is 1 1, vector space homomorphism. Now it is already 1 1, F of V shall go to V. So we have proved this, we have shown since it is a 1 1 mapping, so this shows that F is on 2. Now suppose you take F is on 2. Dimension of V I'm taking n because it is a finite dimension vector space, and this I'm taking to be the basis of V. So I take one element, I take two elements in V. I have to show 1 1, so I took two elements in V, so this can be written as this. So F of V1 equal to F of V2. My aim is to show V1 equal to V2. So this can be written as this, and this can be written as this. So since F is a linear transformation, it will go inside. So we have alpha I F of EI equal to summation I equal to n beta I F of EI. Now this F is on 2, so there exists, since F is on 2, there exists EJ belongs to V. Okay, there exists some EJ belongs to V such that F of EI is equal to EJ for some J. So in place of F of EI, I can write EJ because it is on 2. Okay, means since it is on 2, that it should be sent to some element in V. So that element I'm taking as EJ for some J. So we have here EJ, and here also is J. So we can bring this one to this side, so we can take this out. Summation we can take common, so we have alpha I minus beta I EJ is equal to 0. Now this E1, E2 till En are the basis of V. Okay, are the basis of V, so they are linearly independent. So that shows that the scalar should be 0. So we have alpha I minus beta I should be 0. Okay, so we get this to be 0. Now you bring this one to this side, we get alpha I equal to beta I. You multiply with E1, E2 and take the summation of this, so we get summation I equal to 1 to n alpha I EI equal to summation I equal to 1 to n beta I EI. Okay, so this is nothing but V1, this is nothing but V2. So we have shown that V1 equal to V2. Thus it shows that F is 1 1. Hence the result. Thank you.